Yeah, hello already to everyone who joined. We will not start right away, so we'll wait a few minutes for people to join in, and then I will start with the general introduction. Okay, then let me start with the general introduction. So first, I want to welcome everyone who's already here for this new iteration of the FHI-aims webinar series. And today, the webinar is on multiscale modeling with explicit embedding approaches in FHI-aims. And we again have two great speakers here today, Andrew Loxdale as well as Gabriel Bramley. And a short introduction for both will follow. So let's go first with the agenda. So for today, we have two talks, and the first talk will be by Andrew Loxdale on embedding approaches for multiscale simulations of solid-state systems. And Andy has obtained his PhD in chemistry at the University of Birmingham before becoming a postdoc as well as a Ramsay Research Fellow at the University College in London. And then after, he went to the Cardiff University in the UK, where he's now also reader since 2024 in catalytic and computational chemistry, as well as the co-director of the Cardiff Catalysis Institute. And Andy really is an expert in computational modeling of catalytic materials, both in software development. So he's a contributor to not only FHI-aims, but several other software packages in his group as a whole, as well as a chemical materials simulation in general. So he will have a 30-minute talk, and then we'll have a 15-minute Q&A session afterwards. Then we'll come to the second talk of the session, and this will be by Gabriel Bramley. And he will talk about QM in QM embedding with the Embassy Pythonic wrapper. And Gabriel obtained his PhD in 2021 at the University of Southampton with Professor Chris Scalaris. And since 2022, he has been a postdoc in Andy's group at the Cardiff University in the UK. And Gabriel is also an expert in implicit and explicit solvent modeling for surface science, and not only with his very recent work on this Embassy package that he will showcase you in the second talk. In addition to the two talks for today, we have also tutorial sessions. So you've seen on the webpage for the webinar that you were able to sign up for a discussion and hands-on session 1 as well as a session 2. So session 1 will be in the morning at 9 a.m. while the so Central European time, while the session 2 will be at 4 p.m. Central European time. If you are not familiar with FHI-aims, it might help to watch our very basic introduction to FHI-aims on YouTube in our MS1P EV channel, as well as the Slack channel for specifically we made for this FHI-aims webinar series, where you can ask questions and we can discuss also further in the tutorial sessions. So once again, this is important to note. This is, of course, welcome for everyone. So even if you're not just interested in running the calculations and the tutorial, feel free to join and ask questions of any kind. Several of us will be also in both of these sessions, so you can ask questions related to FHI-aims and the webinar content specifically. And you still have time to sign up. So in case you have not signed up for the tutorial sessions, please do so. You can still do so today, and we can still send you the login credentials and so on for the compute cluster we will use. All the others who have signed up should have gotten an email concerning the tutorial sessions this morning. So hopefully this all works. And the link where we will host the sessions tomorrow is the same as today. So you can simply save this webinar link once again for the tutorial sessions tomorrow. Okay. So without further ado, let's start with the first talk once again by Andrew Loxdale on embedding approaches for multiscale atomistic simulations of solid state systems. So Andy, please go ahead. Feel free to share.
Thanks, Konstantin. Great. So hopefully you should be able to see my screen. Thanks again for the introduction, Konstantin. That was really good. Thank you all for you coming along today. I really just want to start by advocating as well for the hands-on session, which is running tomorrow. It's a really great opportunity to apply the work that we're going to talk about today. So, as Konstantin said, my name is Andy Logsdale. I'm a member of academic staff at Cardiff University in the UK. I'm going to talk today about embedded cluster multiscale modeling. I really want to kind of link the concepts of multiscale modeling with the functionality and capabilities of the FHI-aims code. But to do that, we need to take a couple of steps to build up our understanding about why we would want to do multiscale modeling, and then we can think about the techniques that we can access. So the starting point, if you like, in the challenges we want to address, and here I've framed this discussion point around catalysis, but one can easily think about it for materials design as well, is about the quality of methods that we want to use or the accuracy that we want to achieve when we're modeling materials. And I think it's fair to say now that there is reasonable ability to predict ground state properties for systems with accessible methods. But there continues to be real challenges with out of equilibrium structures. So here on the screen, I've got a transition state in some zeolite catalysis chemistry. So zeolite's a porous material, and we're looking at just a transition between a reactant and product on the left-hand side, where we're moving a methyl group between species. And on the right-hand side, just taken from work from 2019, is a graph plotting out the errors that we get when we simulate this process. The errors in terms of the transition state energies for a range of different methods of electronic structure methods, electronic structure theory, ranging from DFT through to quantum chemistry. And what you'll see is that some of the very popular methods, so on the left-hand side, PBE with a dispersion correction, have a relatively high mean error, so mean absolute error or mean squared error. And that number drops down as we go to hybrid levels of DFT and then on to, say, perturbation theory. So what does that tell us? That tells us that if we want to accurately model chemical processes, then we need to be able to use high levels of theory. We can see that even with the simplest molecule that exists in terms of a chemical sense, which is H2+, where we know what the energy landscape looks like for this molecule. So it's plotted with a black line here. But we know that, for instance, for popular methods such as LDA and even contemporary meta-GGAs, that there is poor representation of the energy of the system as we extend the bond length. So to come back, we really hear what I'm saying is that the challenge we're trying to address is that we want to use high-level methods to study the chemistry that we're interested in, to be able to give ourselves accuracy. And this is particularly relevant for these out of equilibrium structures. Of course, there's another problem, though, that we need to, another aspect of this problem, which is that the scaling is against us for these methods. So one of the reasons that density functional theory is so successful is that it has relatively good scaling compared to more accurate higher levels of theory. So on the graph on the left-hand side now, we show the relative calculation time factor, if you like, for DFT relative to hybrid DFT, perturbation theory, and then coupled cluster. And what you can see is that clearly that as we increase the number of atoms on the x-axis, then the scaling factor increases significantly. And so if I have a material system with, say, hundreds of atoms in my unit cell, then it becomes very unfavorable to perform the high-level theory calculations that we need to perform to get accurate results. There's another aspect to this conversation then, which is that we want to reduce the number of atoms in our system and be able to give ourselves accurate representation. So we've already said here that we want to use high-level methods, but we need to find a way to make that scalable. So how do we reduce the number of atoms to achieve that? Well, if I take the two paradigms, which are at the far ends, if you like, of our modeling world, we have a periodic system on the left-hand side, which, again, this is a zeolite material. So this is just the unit cell, 230 atoms for this zeolite. And the yellow atoms represent just a repeating part of that unit cell. And I know, for instance, that this system I can represent correctly in terms of the electrostatics in the long range. But I've got challenges. I don't have access, for instance, to a vacuum level, so I can't absolutely align electronic levels. I also have challenges with charges if I want to introduce charges into this system. And of course, it's got a lot of atoms, so that's preventative for using the high-level methods. But on the right-hand side, I could take a molecular fragment from this model, and all of a sudden, I now have something where I can access these high-level methods because I've got a small system that I want to model, and I've also got access to vacuum levels. But there's a problem because I don't have access to the electrostatic environment, which is necessary for a bulk representation. And so one of the things that I'm going to introduce here alongside different types of techniques is what's called an embedded cluster method, where you effectively look at representing a material system as a very large molecule with an embedding electrostatic environment. And that allows you then to apply a kind of onion-like structure to your calculation hierarchy. So you might have in the middle, in this representation of a zeolite that I've got in the middle, in the little green atoms there in the middle, I've got maybe a quantum mechanical representation, then some slightly coarser molecular mechanical, then outside that some electrostatics. So let's look at that in a bit more detail. Let's see what that looks like. So here's some range of different materials that we can consider. So on the left-hand side, I've got molecular crystals. Now, there is no explicit bonding between these systems, and so they're perhaps the easiest to represent with this approach. Zeolites, we have what we would call kind of heterovalent, covalent-esque bonding. And then on the far right, I have ionic materials. And I've contextualized these again with catalysis. I know today my title alludes to solid-state embedding, but we're thinking about the design of materials for catalysis, and hence that emphasis on a reaction site. Because a reaction site lets us think about a site of interest in these systems. So if we're thinking about, say, for instance, a dopant or a defect, we can focus on that as the center point of our system. And all the way through this, we've got increasing degrees of electron redistribution. So what I want to talk about as we go through today is about how we tackle modeling these different types of systems. To just dwell a little bit more on what a multiscale QM-MM simulation looks in entirety then. So here on the screen, I've got a representation, if you like, of my QM-MM surface that I've alluded to, and it's an embedded cluster model. So let's build up the shells that we want to talk about. So here in the middle is a quantum mechanical active site. This is some part of the model which I'm going to represent with electronic structure theory, density functional theory, hybrid DFT, maybe perturbation theory, or upwards. All of these are methods, for instance, that one would typically use from FHI-aims. And here's a representation of what that might look like. So here's a good example. This is for a zinc oxide surface where we've got a localized charge. That's what the yellow sphere is. That's caused by a dopant that's in that surface, which is the pink aluminium species. Around that quantum mechanical region, I have an interface. And now the interface is probably one of the most important parts of the entirety of these setups, and really where the strengths of high quality quantum mechanical software comes in. And I'll dwell on that a bit more in latter slides. Around that, we have then a molecular mechanical region in the classical QM-MM setup. So I might have quantum mechanics on the inner, then interface, then a molecular mechanics region, which can be responsive to structural changes in the quantum mechanic region. And then around that, I'd have a frozen region, which effectively preserves the long distance structure and integrity of our system and material that we're modeling, and also provides some kind of electrostatic embedding. So these might be point charges with formal charges. And then right on the outside, I have some additional, if you like, charges, which are introduced to ensure that I have the long range eVolt summation correctly represented. So that's the long range electrostatics in the material of interest. If we're to convert this kind of pictorial representation into a mathematical representation, here I've effectively done a bird's eye view of the image that I just showed you previously, and QM here refers to quantum mechanics. The interface I've put as PPs, that's pseudopotentials, and I'm going to explain those as we go through. Our formalism, like from a mathematical sense, is a combination of both the quantum mechanical energy. So here I've got a contribution which includes both the quantum mechanical Hamiltonian, and then also the electrostatic contributions from both the short range, so that might be the pseudopotentials, and the long range, so that might be the electrostatics that I referred to in the environment surrounding it, plus then a summation over all of the different contributions from the nuclear centers. And then we combine that in what's called an additive form in this work with the molecular mechanics contribution. So this has some terms which refer classically to single, two, three body, and so n body terms representing the energy of the system at a distance from our active site. And then there's also a term in here which we introduced for polarization. So this is to compensate for the fact that, for instance, we have a finite radius of atoms that can move during any calculation that we might perform, up to the distance where you get to the edge of the yellow sphere in the image I've shown you. So for instance, for a material which has got a high dielectric, and so atoms are a long way from an absorption site or a defect, you might find that this correction will be larger because the polarization would be stronger. All of this work that I'm going to talk about, we've pursued in a software package called ChemShell, and I've picked up there Tom Keel, who's really the lead developer of ChemShell, and I've worked with for some time. ChemShell is a package which enables us to perform these calculations, and actually, probably it's more valuable here for me to look inside it and tell you a bit about what ChemShell does and so how it works, so you can then start to conceptualize how you build these calculations. So if you like in a calculation with ChemShell or with any QM method, what one needs to do is one needs to have a method where you effectively get some bulk structure to start with, and you take the coordinates and charges from those and feed it into some object which is going to manage data communication between both the molecular mechanics and the quantum mechanics codes that you want to operate with. It's challenging to implement all of the energy evaluation requirements in one software package, and that's why something like ChemShell is necessary to connect together these different objects, but also manage the structures and energies and derivatives as you work through. So in this context, what we might have is some kind of a driven process where ChemShell asks molecular mechanics driver, say for one of these popular packages, for some energy as a function of the coordinates and a potential. These are fed back, and then that's combined with the information that one gets from a quantum mechanical driver for the coordinates of your system, specifically thinking of that active region aspect of that. This is done iteratively, and of course, then there's a optimization process or other type of evaluation of the energy landscape that one can pursue. So here we might look at, say, energy barriers. And then one iterates through until you reach convergence. And so here what one has to think about is not only do you have a typical optimization process that you might have for a calculation, but you also have optimization in two different regimes. And one of the challenges really is getting the energy landscapes of these systems to be commensurate. How does FHI-aims fit into all of this? Well, FHI-aims really has two roles and two real strengths, if you like, for these calculations. One of the great strengths of FHI-aims to start with is that it provides you an identical framework to perform both periodic and molecular calculations. And so what that means is that we can perform this initial calculation of a bulk system with a software package like FHI-aims and know that we can generate a structure which will have minimal stress in that system and therefore ensure truly representative material properties when we calculate it. And then we can also use that as a driver. So when we evaluate the molecular system using our periodic our embedded cluster, we can then use FHI-aims to do an evaluation of the energy and derivatives, and of course, other evaluations that you might want to do of the properties of the system or that quantum mechanical region. So AIMS is particularly powerful in that space. Now, I spoke before about different types of systems that we can study. And now what I'm going to follow with is just a couple of examples of the systems that we have studied with this type of setup to give you a flavor of the kind of things that we can do. So the first kind of system I want to talk about is a covalent type system. So here what I've got is an example is an interface in a siliceous system, a zeolite system, if you like. And on the screen in front of us, I've got a quantum mechanical region on the right and a molecular mechanical region on the left, and the interface between them. And I said these interfaces are really crucial because what one has to think about is that the electron, the wave function of it, has to be localized within this quantum mechanical region. So we're breaking a bond between that silicon and oxygen, which is represented here, when we create our QMMM model. So we need to compensate for that somehow. Now, the classical way that this is managed is via hydrogen capping at the interface. And what that allows us to do is then ensure the integrity of the bonding of the oxygen species there on the right-hand side, but also ensures that we can have a kind of a controlled interface with the molecular mechanics region. And here I've represented the molecular mechanics now with Qs, which represent the charges on atom species. In an FHI-aims sense, these Qs are what we call multipoles. And so they're functionality which is available in FHI-aims, and we can evaluate properties of these systems and contribute them and include them in the Hamiltonian. And they're very simple to represent. Here we have a representation from our geometry file where we might have a multipole which has the X, Y, and Z coordinates, the order of the multipole, so in this case a monopole, single charge species, and then the charge on it. So this is a chloride ion when I was preparing this presentation. So these multipoles are our way of ensuring the integrity of our model. We can then take this forward and start to think about the system we want to study. So here is a couple of examples. This is firstly for a system for electrochemistry. So this gold on boron doped diamond. This is work done by Shayantan Chowdhury in Warwick, who's in the top right corner there. And what we had is a model of an oxygen terminated diamond surface, which we optimized with periodic DFT. So we did some global optimization to get the ground state configuration of the oxygen. We then took this to the QMMM representation, and we performed a multi-scale calculation with FHI-aims and with COL. And what we were able to do in this type of calculation was evaluate the strength of absorption for the gold species on this surface. So I'll just talk you through this slide. It's a little complicated. So here we have the pristine surface. So this is depth of the surface downwards, and this is our oxygen termination on the surface. And what we have is an absorption energy, lateral and top-down view here, an absorption energy of minus 0.3 eV, which is relatively weak, and charge transfer to the surface. We're able to evaluate using high-level DFT, so hybrid DFT, how this changes as a function of the surface termination. So here we have hydrogen terminated in the presence of an oxygen vacancy. And we also have the boron doping. So boron doping induces a charge carrier. And you can see here what this looks like. And we were able to evaluate this at different depths on the system. And what we found is that the oxygen vacancy obviously improves the strength of absorption, but has a completely different effect in terms of the charge transfer to that of the boron dopant, which also improves the strength of absorption. So if you like, anchors the gold, which is beneficial if you want distributed single atom species, but also leads to significantly different charge transfer. And we wouldn't have been able to achieve this without using the QMM because hybrid DFT applied to the surfaces we were looking at would have been highly expensive to explore across this. We could push this a little further, and actually what we did is we then looked at some of the mobility of the gold species across the surface. And what we found is that we could then perform calculations, and I'm going to refer to these specifically, the bottom row here. We could use different methods, including hybrid DFT. So here we've got HSCO6 and HSCO3. And we could look at the mobility. So the blue box here is going left to right across your screen. The purple box is up and down. And we actually found in this particular case that we had particularly interestingly agreeable GGA and hybrid DFT calculations. Now, what some might say, this is contrary to what I introduced at the start, which is the challenges with representation of transition states. But I think our feeling was, particularly in the idealized systems, these are very weak interactions. Perhaps there is something here, though, which is a fortuitous cancellation of errors, which leads to such good agreement for the hybrid DFT. But irrespective, what it shows is that we can use the hybrid DFT to explore this landscape. So this is quite challenging calculations. Another example case, so this one now I'm looking at the zeolite systems I introduced at the start, and actually up on the top right-hand side is Gabriel, who will be speaking after me, And Gabriel was looking at some zeolitic chemistry. So we're looking at reactions now to convert methanol, which is ideally a green feedstock, so it can come from biorenewable feedstocks, and turning that into portable liquid fuels so that we could use, say, for instance, in long distance travel. What Gabriel was able to do was to use here to study the reaction mechanisms, and I'm not going to dwell on this other than saying there's a range of reaction mechanisms here. But he was able to study the periodic system using a reasonable level of density functional theory, then transform that to our covalent QMMM model. He was able to bring the coordinate system into this model. And then we were able to evaluate the quality and the impact of the different density functions that we used. So here, actually, what we're doing on the left-hand side is we're comparing the reaction energies for a GGA and a hybrid DFT approach. And we're looking at the errors that we get when we combine the two methods. So what you'll see is that effectively there is some errors we transferred across to clusters, and this can be addressed a little bit, if you like, by by representing the system with a slightly larger unit cell in our periodic models. But also that there was a plus minus relatively similar for the functional choice. So this was, as I say, going from GGA to a hybrid level of theory. But if I look at the reaction transition states, so the energy barriers, here you'll see that there's a much greater area associated with the representation for the density function that we used. So what this tells us is that in this case, we're able to use QMM to really access the high level theory that we need to be able to get correctly the transition states. And in a reaction chemistry sense, transition states determine, or the accurate representation determine the rate of reaction. So they're really important for us in terms of deciding if something's going to be catalytically effective. So that covers the couple of covalent systems I want to cover. I now want to just introduce what we might do for an ionic system. So here we've got a slightly different case where instead of charge electron sharing, we have charge transfer. So in this particular case, we use what we typically call pseudopotentials, or you might call effective core potentials in, say, a Gaussian-based code. And what these do, they provide a representation of the charge distribution at the interface on a species which is just on the edge of the quantum mechanical region, but not represented explicitly by the quantum mechanics. So we put these on the bare cations explicitly to represent the core electronic structure. And that's to prevent, for instance, electrons jumping onto that exposed positive charge, which would be favorable for them. In FHI-aims, we've realized this with numerical pseudopotentials in the work of Daniel Berger. And these take a form of Kleiman-Bylander. So here what we have is a local contribution. So this bit here, which is contributed, if you like, on the global grid, goes into single electron Hamiltonian. And then we have a non-local contribution, which is dependent on some angular momenta. And this we compute separately across all of the different angular channels. This is implemented in FHI-aims, has efficient performance and such like. And there's a really, and just to say that this is what that looks like as an input file. Again, very accessible, well documented in the manual. And we effectively have a term in the geometry file which gives the name, the XYZ coordinate, and then the type of species this is represented by. We will use this originally when we worked on this for water splitting on titania. And Daniel showed very quickly that actually the importance of having these pseudopotentials. So on the left-hand side here, we've got the density of states for a titania surface. So this is a free cluster. And what you can see is that the occupied states, which are represented up to here, this -5, that give you no band gap, which is, for those who know titania, obviously incorrect. Titania has a band gap of about 3 eV, slightly more. It's a rutile surface. So we've got the charged neutral surfaces and we've got some oxygen termination, but we clearly have incorrect electronic representation. But if we introduce these pseudopotentials, then what we get is a band gap, and this matches with the slab model that we were working with originally. So here you will see the correct band gap representation. So here we demonstrate how important those pseudopotentials are for correct electronic structure representation. Now, what we're able to do with this then is look at some of the intermediates in water splitting. And here we've got the periodic boundary condition model for GGA type calculations and the absorption energies for some of the key intermediates, the free cluster, and then the correctly represented QMMM embedded clusters. And what I'd like you to draw your attention to is that this number here, so the larger surface, if you like, that we use for the periodic boundary is different to the smaller cell, which shows finite cell effects, but also that our QMMM with the correct embedding agrees almost ideally with this. So what we really show is how we can reproduce these periodic models and also give ourselves access to very high accuracy. We built on this by then looking at a range of really high level accuracy functionals. So the previous work I showed you there was lower level GGA type work. And now all of a sudden, what I'm looking at is the absorption energy of these different intermediates as a function of the functional that we represent this absorption with, all the way up to what's called here double hybrids, all of this within FHI-aims. And I think the important thing I want to stress in this and the interpretation we can take home from it is that the rate determining step, if you like, the strength of the absorption, so what might be the rate determining step, changes as a function of the different type of functionals we use. So here we have purple as being, so the absorption of the peroxide species, which is the weakest, if you like. But then if I go across here, the peroxide shifts down. And so this really then makes a big difference in terms of the way that the rates of this reaction might occur. The final example, I've just got an eye on the time. I think I've just got time. Final example I want to show you. So again, here I'm going to talk about surfaces. So this is a complex chemistry surface model, but I assure you we're not going to dwell on all of the organic molecules on the screen. This is with Dave Willock, who's a member of a colleague of mine at Cardiff University. So Dave is really interested in taking glycerol, which is this thing here, which is a biorenewable feedstock, and turning it into valuable chemicals. And what we're particularly interested in the work that we're looking at is looking at how we go from this step where we have a radical species across to a final product species here. And so this has some hydrogen transfer chemistry involved to be able to turn that molecule. Now, what Dave and colleagues and experimental colleagues found is that we could do this with magnesium oxide very well. And we wanted to investigate what that reaction looked like. So we studied this on MgO. So here's the reaction process again for this step that we're talking about. So this hydrogen transfer, if you like. Here is a periodic DFT, and this is a QMMM, and this is really just to show you that the frontier orbitals are identical in these systems, so we have a really good representation of the system. And with the hybrid DFT, what we could do is we could investigate how this reaction profile looks like as a function of different types of sources for the hydrogen species, which is this part here. And what we were able to find is that we could identify what would be the most stable product species. So here in this case with formaldehyde forming from these species up here. And so this really gave us a good insight. But one of the key things I want to stress with this is that actually what we also found is that we could change the shape of this QM region effectively to be able to give us the easiest way to perform the calculations we want to do. So these are quite large molecules that we've got on the surface. And actually what we found is that we could focus very much on the planar representation of that QM region so that we can maximize the quality of the absorption representation rather than focusing on the depth of the model, which is a stereotypical way to do it, if you remember the onion-shaped model I showed you at the start. And that brings me to the end, to the complete summary and acknowledgements of my work. So what I just wanted to present today, and I hope I was able to communicate, is that we can use QMMM, and particularly we can use it with FHI-aims to discretize problems into areas of high and low accuracy, which really allows us to focus computational efforts where we need to, so we can understand both complex catalysis, as I've talked about, but also materials. And I'm very happy to share some other literature where we've worked on this kind of problem, studying defect chemistry and materials design. For covalent embedding, we use link atoms, which include near distance bonding environment, and there's some representative links there. And then for the ionic embedding, we use pseudopotentials, which very effectively allow us to represent this accurate electronic structure at the interface. Some final acknowledgements. So the people in bold here are the ones whose work you've seen on the screen. Gabriel, you'll hear from shortly. We've got Marla and Dave also at Cardiff. I want to particularly recognize the contributions from the team at STFC Daresbury, who manage Chemicals. So that's Yulu, Tom Keel, and previously Paul Sherwood. Long-term collaborators at UCL, especially Alexei Sokol. Strong support for many years from the Fritz Haber Institute and from Munich, from Technical University of Munich, and from a colleague at Warwick, now at Vienna as well, Reinhard Murer. Thank you all for your attention. I'm very happy to take any questions.
Thank you so much, Andy, for a very nice talk. Thank you also for staying on time. And now I would open the field to questions. So as attendees, you will see in your Zoom taskbar down below a Q&A button. So please feel free to simply enter your questions and we will try and answer them one by one. So there is already one question in the chat by Katarina. And the question is, how are the pseudopotentials designed / optimized to get the correct density of states?
It's a very good question. So I'm gonna describe this in two ways. Okay. So the pseudopotentials as implemented in FHI-aims, which I'm going to start with, are calculated with respect to the gas phase ion. It's an it's a atomic solution, spherically symmetric, with a software package actually, which forms part of the legacy, if you like, of FHI-aims from many years ago. So they are not optimized. They are accurate for the ionic species that we want to represent in the gas phase. So what's the benefits of that? That means that actually we're able to represent something accurately, in that we can solve the Schrodinger equation, give ourselves a representation for that, to match the potential for that. What's the downside? Well, then we don't necessarily have something which may be representative for a specific system we're interested in. And of course, here we've got a problem of portability versus suitability, if you like. The reason that I've kind of framed it around this, well, I'm going to give you two answers, is because I want to talk also about the alternative, which is that, so prior to the work with FHI-aims, this work was almost entirely done with Gaussian effective core potentials. Now, effective core potentials are designed with a basis set to represent the valence electrons, but in an ionic species, you lose those valence electrons. So you have a change in the representation of that core potential. So actually, what we found in the previous work is that the Gaussian ECPs weren't necessarily accurate because we were changing the representation by getting rid of the basis sets. And that led to errors, which meant we had to tune them to the materials properties that we're interested in. So effectively what we were doing then, effectively doing a global optimization problem, if you like, tuning all of the different parameters we have to represent the size of the Gaussians, and then seeing how that reproduces the properties, for instance, the width of the density of states or such like. With the pseudopotentials, what we've tended towards is avoiding that optimization because of the fact that we're basing it on an accurate representation of that ion species. Perhaps the only consideration is we make sure we don't end up with any trapped ghost states, which can occur if you've got a poor representation of the pseudopotential. But other than that, there is no optimization, but that doesn't mean one can't optimize it. So I think that's probably something which is an area where it could be explored in the future if we felt there was something that would be better represented.
Thank you. There was also a quick follow-up from Katharina. She said, so effectively, this only makes your QM region larger without needing to treat all electrons?
Yeah, I think that's a very fair summary of it. So I mean, when we say makes it larger, of course, if there are no electrons, then one can argue that it's no longer quantum mechanical representation. But we're getting into semantics, right? I think the interesting thing here is about what you're touching on, which is really important, is about how we represent the interface accurately, but also affordably. So one could, for instance, and I think Gabriel is going to talk about the next one, can think about at an easy level, we could talk about hierarchical basis sets. So I could say, okay, so I could have a light basis set and then a tight basis set, to use the aims analogy. And that would give me a hierarchy of accuracy before I get the pseudopotentials. Or we could freeze the density representation, which is another space that we've worked on previously. And all of these come with costs and limitations in accuracy. I think personally, once we remove the electrons, then I start to think about it as being something that's not necessarily quantum mechanical, but of course there's angular momentum contributions. But certainly once we get beyond the pseudopotentials, then yeah, you're right. We are then out of the quantum mechanics completely.
Thank you, Andy, for answering the question. I hope, Katharina, with this, you're satisfied with the answer, but of course, you can still ask a follow-up if you like.
Of course.
Yeah, Katharina says thank you. So, any other questions from the attendees? Please feel free. There's also the option, in case you don't want to use the Q&A function, to raise your hand, and then we would also allow you to speak. So that is also an option, if that's what you would prefer to do.
If there aren't immediate questions, I just want to stress that I'm going to stay online all the way through here. I'm happy to answer any questions that are typed into the text as we go through today's seminar.
Yes, thank you, Andy. Just checking the other channels in case something has come up.
Maybe I could just ask one while you do that, Konstantin. So,
thank you.
Does FHI-aims select? So you gave the two examples of embedding, covalent and ionic, where you have different methods to treat the interface. So is this something that's kind of an input keyword to control between the two on the FHI-aims side, or is this something that's done on ChemShell side?
Very good question. So FH-aims is in effect ignorant to the multiscale QM-MM simulations in this context. So one makes the choice, one has to make the choice about the decision of the interface representation external to FH-aims. FH-aims, the terminology we use is a calculator. It effectively takes the structure object and gives us an energy back from it. From a design perspective, I think that some time ago we thought about this and decided it would be easier to manage this externally because of the fact that it gives you the flexibilities I talked about before to go to different types of calculators. So you may, if I jump back a couple of slides, what we'll see is a lot of the other packages, yeah, I'll get there. A lot of the other packages here are actually what we would call Gaussian orbital codes. So they typically they have a similar role in the way that the calculation works, but they also have the same receive the same inputs. So effectively, they receive a structure they calculate the properties of. I think probably one of the advantages of doing this at a ChemShell level rather than inside FH-aims, for instance, about the hydrogen location, is that then one starts having to program in about chemical about the chemistry of specific systems, which loses the generalized functionality of FH-aims. But of course, the detriment of this is that it means that it's not all within one software package, and one has to use multiple software packages. So I think to answer your question, it is fair to say that it is not as simple as just putting something into FH-aims and running the calculation. It requires a combination of packages to perform it. Does that help, James? Is there anything else I can clarify?
No, that's great. Thank you.
Sorry?
Thank you, James, for the question and also the answer, Andy. Let me see. Okay, in the other channels, I don't see a question. Maybe you can comment a bit on because you're specializing more in the explicit embedding side, right, in your work. And I know that there's also been a lot of work, of course, on implicit embedding approaches, also in the context of FH-aims. So maybe you could comment a bit on the differences and maybe why in your specific work you're focusing on the explicit versus the implicit side.
Yeah, of course. Yeah, I think that's actually a really good question. So AIMS has this whole extra kind of space in terms of embedding for implicit embedding. And what's implicit embedding? So implicit embedding is effectively an effective medium rather than a directional kind of explicit representation of whatever the environment is, which is what I've talked about today. And I think maybe I'm aware that I've got the wrong slide on the screen, but I don't really have a better slide to present, so I apologize. One could start, if you like, if you say we talk about effective mediums, by saying, well, why don't I just get rid of all of the atoms that I have in my molecular mechanics reading and represent that by an effective medium? And so what I say is that we need the directionality in bonding because we know that's a property of materials. So to start with, if you like, I want to express that we have the ability to represent the mediums, and that's really important for lots of applications. But in the applications today, I've talked about this very explicit representation of bonding structure, which needs to be covered by, say, for instance, electrostatics or both near and long range. Now, I want to extend on that a little bit, though, to think about, again, we could, for instance, one could imagine having an implicit embedding environment beyond an explicit embedding environment. And also there's lots of really good applications for the implicit embedding model in FH-aims for other uses. So particularly it's really common for use for solvent representation. So in AIMS we have really good representation that we can use for applications in, say, for instance, solvated systems. And the multipole expansion and the Poisson-Boltzmann approaches, which are both part of the AIMS distribution, have functionality which allows you to do calculations of, say, molecules and materials in different types of dielectric solvents, and in some cases allow you to evaluate forces, in some cases allow you to use periodic systems. So there's a real diversity of tools there. What we haven't ever done and what we would be really interesting to do is combine all of those together, so kind of as I've alluded to. So for instance, for a surface, a catalytic surface, if you like, to have an implicit embedding environment around it, or an explicit embedding environment, so some water molecules, and then an implicit embedding environment. But of course, as we've already alluded to in answering James's question, as you introduce these more layers, you introduce complexity and some further things to think about with the design. So I think, sorry, Constantine, I've gone around the houses here, but perhaps to summarize, implicit embedding is a completely different functionality which offers lots of opportunity, specifically, I think, with systems where there is a directionality is less important in terms of the embedding environment. It wouldn't work for the material systems that we've talked about today, but it offers a really good complement to the kind of things that we've talked about in the chemistry that we've covered.
Great. Thank you, Andy, for the nice answer. And as Andy mentioned, in case you still have a question throughout also the next talk, feel free to just type it in the Q&A section. Andy is still here and can also answer via text. But with this, I would like to thank Andy again for your time and in a very nice talk, as well as the Q&A session. So thank you again, Andy. And then I would hand over to Gabriel with the next talk. He was also briefly introduced in the talk from Andy, who will talk about his recent work on the embassy package. So Gabriel, please go ahead.
Hello. Can everybody hear me for a start, just while I spin up my Zoom?
That works, yes.
I'm seeing a nod of the head. Excellent. You're going to see two Constantines, and now you're going to see a slide. Excellent. So yes, thank you very much. Thank you very much, Constantine, for both inviting me and for the introduction earlier. And thank you, Andy, for leading in some of the context for the talk I'm about to deliver now. So we've been working on a QM in QM embedding interface for FHI-aims, which works as an external wrapper for a number of years now. And we're very happy to show you some of its capabilities and how it can help you run simulations, hopefully faster. So as Andy alluded to, higher accuracy methods such as couple cluster and MP2 suffer from quite poor scaling with respect to system size. But sometimes there are observables such as transition state energies or certain transport properties which are not accurately represented with pure PBE alone. And although DFT serves as a good compromise between the two, it doesn't always get us to the answer that we want. And this is where multiscale embedding helps us out sometimes. Now, some of the physical motivation for how we can implement embedding comes from this comes from the nearsightedness principle of electronic structure and electronic matter. So this effectively states that we can have a perturbation of the background potential that a density resides in. And as the density is further and further away from the initial site of perturbation, its effect on the density or the perturbation it'll have on the density will approach zero. And this effectively goes down to the fact that the density will only be affected by potentials in a given vicinity. So this means that we can describe a certain part of our system with a different level of theory without describing a part of our system that we're particularly interested in. So Andy has just gone over what is embedding, and he's gone over what a subtractive scheme is as well, where you essentially just describe a small part of your system with a high level of theory, and then subtract out the corresponding subsystem described with a lower level and less expensive level of theory. So you are describing the boundary between the high level and the low level of theory with the interaction terms of the lower level of theory. And this, Andy was discussing QM-MM, but we should probably go over why you would want to go to a scheme that uses quantum mechanical and quantum mechanical embedding over the classical term. And part of this comes down to a lot of the parameterization that you have to do to get some of these QM-MM models to work properly. So a lot of the errors that come from QM-MM come down to the interface region between your QM and MM regions. And this is largely an artifact of the fact that you're describing two regions of two systems in close contact with each other with fundamentally different physics. And to get accurate results, you sometimes have to parameterize the force field to a reasonable extent to get an accurate energy. And we can see this And we can see this in the number of atoms that you have to introduce for a QM region. So sometimes you have to include hundreds of atoms to get an accurate energy, and sometimes that's not feasible for the more unfavorably scaling methods. So we move on to what we've introduced in FHI-aims, which is projection-based embedding. So like QM MM embedding, where you describe a small part of your system with a high level of theory, you're now describing the wider environment with another quantum mechanical method. So for example, for DFT and DFT embedding, you describe the whole system, both of your super system, with a method 2, as you can see here, and you can subtract out the corresponding region of the active region with the lower level method, and then add in the high level contributions of method 1 described with the density matrix that corresponds, which has been optimized in the embedding potential. And this also can be applied for wave function in DFT embedding as well. So this is where you subtract out the low level of theory described at the DFT level of theory, and then add in an energy contribution from a wave function method such as RPA or MP2. So how does this work in practice? So projection-based embedding starts off with the density matrix. So you start with the supermolecular density matrix, which is described through the molecular orbital coefficients from solving the Cohen-Sham equations. And to get the density of your two subsystems, you localize the molecular orbitals and partition the density into two disjoint subsystems A and B. And this is generally achieved using a unitary transformation matrix or some form of transformation method, such as either a singular value decomposition, or you can use more of an old school method like Pipek-Mézet or Edmondson-Rudenberg to move from the canonical Cohen-Sham wave functions to localized wave functions, which you can then select based on where they lie in your system and whether they're centered on the region of interest or whether they're concentrated in your environment. And projection-based, because it's called projection-based embedding, you can quite rightly surmise there's going to be some form of projection involved. And the way this is accomplished is using a level shift operator, as shown here. And effectively, what this does is it takes the density associated with region B. This should be superscript B, apologies, and shifts the molecular orbitals associated with subsystem B to a region to the higher part of the energy spectrum. So this mu value here is generally 10 to the 6 high Chartree, so it moves all of the molecular orbitals associated with subsystem B far, far above the virtual orbital space you would find in a typical calculation. So in effect, when you perform the Cohen-Sham, when you use your embedded, when you solve your embedded Cohen-Sham equation, you will never optimize into that region. So you maintain perfect orthogonality between subsystem A and subsystem B. So this all comes together in the projection-based embedding scheme where you construct the embedded Fock matrix. And you use this to find density matrix subject to the high level of theory. So you can either use the same level of theory, a GGA, or you can use a hybrid level of theory. And you construct the embedding potential as such. You take your supersystem Fock matrix, you subtract out the lower level theory contributions, and you add back in the Fock matrix, which corresponds to the high level of theory density. And once you've put all of these terms together, you can then solve the standard Cohen-Sham eigenvalue problem with this new density, with this new embedded Fock matrix to obtain the density matrix of the high-level embedded subsystem, and then just bring all your energy terms back together, and then you have your DFT and DFT or wave function and wave function energy. So this is all well and good, but as you've probably surmised, you have to perform 3 different calculations. And in as many electronic structure codes, generally have a monolithic design as such, where you can just treat them as a box where you put in input and it performs a self-consistent field calculation and it calculates the total energy. To have QM and QM in many electronic structure codes, you have to put a lot of the machinery of embedding into the software, and you also need a high-level wrapper that calculates the different subsystem energy. So, for example, you would need a routine that takes in this energy and then calculates this energy and the density matrix, partitions it, and then calculates the subsystem energy. And as you can imagine, this becomes very complicated in fairly large electron structure codes, where many variables are defined at the beginning of the calculation from the input file. And this is a fairly unsafe way of coding if you're essentially changing not only your level of theory that you're calculating, but also which part of the geometry that you're interested in, and different matrix extents that you would have to allocate and reallocate and deallocate. So this is why we went for something which is more modular. So instead, what we've done is we've gone for a Pythonic style wrapper, where we define our inputs using something like ASE, and then we use an interface, or a C-based interface, which I'll come into later, to call FHI-aims as a library. So we can then calculate the supermolecular system, we can then perform the partitioning in the Pythonic wrapper, and we can then call the subsystem calculation to the low level of theory, and then we can calculate the embedding and projection matrices, and then calculate the final high level energy. And what we hope this does is create something which is a little more reusable and can be extended to other codes. And not only this, we can apply this to other forms of QM and QM embedding. So Dando Chavez, who I've worked with on Embassy, has also implemented a frozen density embedding theory implementation that works with aims as well. So other forms of embedding are implementable and they're available in Embassy. And the glue that holds all of this together is the ASI C-based API. So what this does is it allows you to take the data structures I was talking about earlier, so the density matrices, the Hamiltonians, the Fock matrices, and communicate them back to the wrapper using C pointers. And the advantage of this approach is it allows us to place in information and take out information from FHI-aims without resorting to a file I/O mechanism. So we can just keep everything in memory. We can perform copy operations if we need to, or we can just use the C-based pointers without deallocating them in the code. So this saves us a little bit of trouble in the sense that we're not shuttling information to the disk, which is hopefully a little faster. So overall, the Embassy workflow looks a little like this. So you initialize your inputs and define your ASI callbacks. You gather the density matrix of the total system. And this involves calculating the low-level reference Hamiltonian. You take back your electrostatic embedding for the whole system. And then you localize, divide your density matrix into subsystems A and B, calculate your embedding potential by calling the low level of theory onto the active subsystem, and take the electrostatic matrix back from there. And then you calculate the projection matrix from the environment density matrix, and then use all of these terms together to calculate the final density calculated at the high level of theory to give you your total energy. So now that we've explained all this, we can now move on to some of the test cases. So a lot of the test cases that we used are simple systems, but what I'll also demonstrate is some of the scaling to more complicated and slightly more sophisticated systems. So let's start off with the pentanol dimer. So this is embedding a pentanol dimer with a small active region of the two OH moieties, and we are measuring the dissociation curve as you move these two pentanol dimers further away from one another. And generally, what you want to do is you want to take the normal PBE calculation, which is calculated for the supermolecule, and then compare this for PBE and PBE. And what this does is it gives you an absolute baseline. Does this work? And if there is an error at this level with the given orthogonality constraints that you put into the system, you can pretty much guarantee that there's been some kind of bug introduced into it. But luckily here we have PBE and PBE embedding working. And then something a bit more interesting, where you have PBE naught in PBE embedding. We see a small error of about 0.2, 0.3 kilojoules per mole, but this is well within accepted bounds of accuracy, I would argue. But we run into a little bit of trouble when we start running RPA in PBE embedding. So what we have here is RPA at PBE and an error of about 10 kilojoules, 9 kilojoules per mole at the closer extents. And this, although it decreases over distance, at the equilibrium distance between the two PBE pentanol molecules, we end up with an error of about 3 kilojoules per mole. But we can ameliorate this error by increasing the size of our active region. So what we have here is the result I just showed you with a little bit of a speed up, but the speed up is pointless in this case because we're essentially far above reasonable bounds of accuracy. But as we increase the number of atoms that we include in our active region, you also decrease this error for RPA. And although this moderates the speed up slightly that you get for RPA, we can keep doing this. And we roughly get to a reasonable level of accuracy at around the second or third nearest neighbor from the oxygen moiety. And you get some moderate speed ups for free with RPA. This is not necessarily the case with GGAs and hybrid functionals, mostly because you're still performing integrations across those basis sites in the original implementation of QM and QM embedding. Whereas with RPA, when you decrease the size of the active region, you're increasing the size of the virtual orbital subspace at the expense of the occupied subspace. And given that it scales n to the 4 based on with two of the n terms being the virtual and the other one being the occupied, you end up with a more favorable scaling the smaller you make your active region. So we get this speed up for free with RPA, which is very nice. So as I just alluded to, when we include, for the form of QM and QM and projection-based embedding that I just presented, all of the basis functions are included in the high-level calculation and all of your subsystem calculations. Now, we know from the nearsightedness principle, and we know that some of the charge contributions to the active subsystem are not going to be all that important. So we know there is very little charge from the active region, especially if we localize our charges that reside within the environment subsystem. So what we have here is the ghost atoms that you would see ordinarily in a calculation. But what we can do is we can use a form of basis truncation which removes ghost atoms from the environment that we're not interested in. So in this case, we use a Mulliken-based threshold that essentially tells you, given a charge criteria tau, whether we're interested in a ghost atom. And if it doesn't contribute a significant amount to the inner active region, then we just exclude that basis center and we remove those basis functions. So let's go with the example that I've just shown. So this is an organic acid dimer. And what we have here is effectively what happens when we decrease the truncation threshold, which is measured in standard charge units. FHI and eager among you may notice we say chemical accuracy here. I'm not too happy with that label, to be honest. Just treat it, because we're measuring this relative to the full PBE calculation or the full PBE naught calculation, but just treat it as a rough threshold of about 4 kilojoules per mole accuracy. And what we see is, as we decrease the threshold, make it tighter, the error in the dissociation energy between these two dimers also decreases. So we go from 10 to the 4 kilojoules per mole, which is a crazy level of error. And as we decrease the threshold, we end up with something a bit more reasonable. So about below that 4 or 2 kilojoule per mole threshold. And what we see here for PBE are some moderate speedups, but nothing that's going to break the bank, nothing that you would incur this level of inaccuracy for. But as you increase the number of, so as we go to PBE, we see that the scaling, as we increase the truncation threshold and we decrease the number of basis functions that we include in the high-level calculation, we see much more favorable scaling. So our calculation, so the high-level calculation in this case is 3 times faster than the untruncated form over here. And as we move to RPA, this is where we start getting the most dividends from the speed up. So we take, so when we go to the level of truncation that we're interested in, we can get up to 15 times speed up for the high level calculation. And as RPA is probably going to take the lion's share of calculation time for systems of this size, we would probably consider this as reducing the big headline number in terms of wall time, while also keeping within a reasonable level of accuracy for the dissociation energy. So we've gone through these toy systems. That's all great. That's all well and good, but they're not really where the strengths of QMMM are the most obvious. So what I want to show you in the last 10 minutes of the talk is the advances we've made in introducing infrastructure to make Embassy a bit more scalable. And this includes MPI support and Scalapack support for some of the linear algebra machinery that operates within Embassy. And to do this, we're going to take what Andy was showing before, some of these zeolitic systems. So in this case, we've got a hydrogen-capped zeolite of about 686 atoms. And we can demonstrate that these calculations can run fairly well. And the reaction, and the observable that we're going to measure everything against, is the reaction energy of this reaction here. So this is methanol to DME. So this is the bringing together of 2 methanol molecules on this zeolitic acid site to form DME, which is a key initiation reaction within the methanol to olefin process. So first, let's just demonstrate that we're reasonably scaling in terms of memory with these large matrices within the Pythonic wrapper. And we can show that we're indeed accomplishing this. So as we take this 686 atom cluster, and as we increase the number of nodes that we assign to the calculation, you get what you expect. You get a decrease in the amount of overall memory usage per core. That's nothing fancy, but it just shows that we can at least scale in terms of memory, and timing scaling also works reasonably well for the linear algebra operations that we perform in Embassy. And also, we hope we have a performant way of mapping between the truncated and full supramolecular basis representations of the density matrix and the Hamiltonian. And finally, just to show a more practical system, we have a PBE naught in PBE embedding calculation for our 686 atom cluster. This is a 3 nearest neighbor active region. So we include the T site in the center, and then 3 nearest neighbors around the central site. And what we have is something that we have to bear in mind. So when we deal with embedding calculations, we have to deal with not just the overheads associated with truncation, but also the overheads involved with embedding. So when you have to converge a number of things when you're running these calculations. And although the reaction energy, as defined here, we're at about 4 kilojoules per mole, which is not a great level of accuracy. So you would probably want to increase the size of your QM region just a little bit. But we find that our activation energies are somewhat performant below this 2 kilojoule per mole threshold. I would consider fine and happy. And the other thing, we have our error associated with truncation. So what we take is, we take this large cluster, we cut out an active region, and then we truncate the basis for a PBE naught and PBE calculation. And for a threshold of 10 to the minus 4, we're getting essentially at negligible levels of error. And on top of this, we get a relatively good speed up out of 10 to the minus out of this 10 to the minus 4 threshold versus the full PBE naught calculation for the total energy. So you can see here, we get about between a 4 to 5 times speed up compared to the full PBE naught calculation for the large zeolitic cluster. So that demonstrates everything that we've been doing with Embassy recently. We have some extra development work going on, but what I'm hoping we've demonstrated is that Embassy can reliably and in a user-friendly way execute QM and QM embedding calculations. And not only this, we can extend the types of systems that we can run RPA calculations for. So for RPA and PBE embedding, we can run those calculations with a relatively minor impact on accuracy. And we've also demonstrated that the framework scales to larger system sizes as well. So atom counts of 686 plus 1,000 atoms. We've not run anything much beyond that because it's frankly not that useful for the systems that we're thinking of. But if you've got a use case for us to really stress out the framework, please let us know. And for future work in development, so spin polarization support, that is on the cusp of being done. That's going to be merged soon. And other work associated with absolute truncation. So not using this parameterized charge-based metric, but using a Friesen Thor style algorithm to optimize the two subsystems separately and then calculate the embedding potential from there. And that should be very, very favorable and very good for our wave function calculations. And then other things in the works. So there's probably more than I can fit on this slide, but as we also have an electrostatic embedding interface through ChemShell in development in conjunction with the project student we had in the summer. And we're also working and tackling the big beast of analytical nuclear gradients for these types of systems, which I'm not looking forward to, but that's just life. So thank you very much. I'd like to thank Andrew Logsdale, my supervisor, Pavel Stashenko for his contributions to ASI and Scalapack for Pi and all of the other 4 Pis that he's worked on. I'd also like to thank Oscar Van Buren, and also not on this slide, but I do want to thank Danjo Chavez for helping me work on some elements of the Embassy infrastructure, which have been, which hopefully we'll see more use out of Embassy soon. So thank you very much. As I said, we'll probably talk about the tutorial and hands-on session led by Oscar, but I'll also be there briefly just to talk about some of the tutorialized elements of Embassy as well. Thank you very much.
Thank you, Gabriel, for a very nice talk. And then once again, I would open the talk to questions from the audience. So please feel free to ask a question for Gabriel. We'll also check some of the other channels in case we have some there.
Maybe I can ask one while people are thinking. So for these, for the basis convergence threshold, do you always have to converge it, or can there be some kind of, I don't know, sensible parameter to choose? And how much is it like affected by the basis set size, the QM methods, and the system?
So in my experience, I find 10 to the minus 3, between 10 to the minus 3, 10 to the minus 4 to be a reasonable compromise. But I think it somewhat depends on the size of your system. I've only really tested between PB NOR and PBE for the truncation threshold, and you seem to get fairly similar behavior between the two. So you converge to a similar place. In fact, we can just show for the truncation thresholds the effect of functional. In terms of basis, I don't believe there is too much of a change, but I probably only checked between the basis thresholds, the NAO 3Z types of basis to the 5Z type basis, and I don't really think there's that much of an effect for the truncation thresholds there either. I think because it's atomic base, I think if you had something which filtered in terms of basis function, you probably would have a bit more sensitivity there, but I think having the atomic base threshold does somewhat ameliorate some of the issues of that.
Okay, thank you.
Thank you, Gabriel and James. There's one question again from Katharina in the chat. In the embedding method you use, you can treat charge transfer from one fragment to the other, right? Does the localization have to be possible through occupied orbitals only?
So there are some localization schemes that deal in the virtual space. They are a little trickier and they converge. They take a little longer to converge, but they do appear to work anyway for simple test systems. For this system, I don't believe there is charge transfer allowed between the two subsystems. So when you localize, you do define the charge that resides on each subsystem, and then you kind of fix the charge, allowable charge for each subsystem. That comes, and you're informed how much charge each subsystems will have just through the localization algorithm. I'm not sure whether that fully answers the question, but I think there are, if you wanted to have more sophisticated like charge transfer between the two systems, you would probably need to look at something like a DFET or something of that nature.
Thank you, Gabriel. Katrina, hopefully that answers the question. Otherwise, feel free to ask a follow-up once again. Andy, I think, wants to maybe chime in. Yeah.
I want to ask a question on top of this, right? So, because it's quite a nice question because it takes you into the space of things like excited state chemistry. Do you have a feel, Gabriel, of the cost to do the localization in the virtual space?
So
relative to the cost of doing the in occupied space. Sorry.
So I think it depends on the extent of the virtual space. Because I believe the localization algorithm that we have implemented in FHI-aims that can deal with the virtual space is on the, I think it scales n to the cubed with the number of states that are included in the calculation. So it will probably get quite expensive, probably on the order of the diagonalization, but these are, again, just these are n state by n state arrays rather than n basis by n basis arrays, so they're not as expensive or as dramatic. But I believe there are excited state implementations, including TD, DFT, and GW-based implementations of projection-based embedding that don't require localization across virtual space as well. So I think they just use the ground state truth of the supermolecular system, localize, and then just perform the excited state calculation on that subsystem in the presence of the embedding environment, if that makes sense.
Okay, helps. Thank you.
There's also, I guess, a comment from Danjo concerning the question. He mentions explicit charge transfer needs DFET, so density function embedding theory, through the Wu-Yang functional. So I guess that's more of a comment related to the question. There's a follow-up from Katharina. So she says, the question comes from the use case for non-insulators. So in principle, it sounds as if the method were applicable, but only if one is sure that the high-level cluster includes all shielding charges in the conductor that may occur.
Yes. So I would probably be a little skeptical about running this type of framework with anything without a significant band gap, because I don't believe the localization will behave in a nice way. So you won't be able to construct a decently localized embedding potential that encompasses the entire environment. You'll end up with like little bits of mixing between the two and a continuous spectrum of states that that extend across your defined environment and active region. So perhaps there is some way to get it to working. I've not really tried with non-insulators, but I think there are schemes which are probably a little more performant than projection-based embedding for that particular problem set.
Maybe if I could just come in for very quickly on this. Sorry, James, just jump in front of you. Of course, Gabriel, the solution here that you're working on is the frozen density embedding, which you haven't covered today, Danjo.
Yes. So the frozen density embedding, and also Danjo's working on the DMET implementation as well, which operates within FHI-aims, and that's probably a bit more performant for non-insulators and systems with small band gaps.
Okay, thank you all. Katharina also says thank you. James, is that a follow-up or is this a new question?
No, follow-up. So kind of on this point on the how to partition the state or the orbitals and occupied and virtual states. So would it also be possible to use something like a fragment molecular orbital approach? I don't know if you're familiar with this, but there is some code in FHI-aims which implements this like fragment molecular orbital method.
There is, and I think in principle that should be possible. I think the framework would allow it. I think it's just a matter of I think it would just be a matter of properly defining the subsystems and then mediating the interactions between each of the subsystems, because there are as in the frozen density embedding, a way of transferring the external potential to and from FHI-aims through file I/O, but we'd need to implement the import mechanism for the Cartesian space embedding potential to have this basically on the same kind of framework footing as a projection-based embedding. But it's still possible with the file I/O and using Embassy as kind of a wrapper just for executing calculations and letting it know where different pieces of the embedding potential are within your file system.
Okay, thank you.
Yeah, I've just allowed Danjo to speak, who raised his hand. So maybe you want to add a comment also.
Hello, can you hear me?
Yes.
So and just want to jump in with what Andy said. So the FDET actually works with no band gaps or metals. I did test it with a cluster on a cluster system for aluminum, and that works at least in that small test case. But the status of the frozen density embedding in AIMS currently is limited to cluster to cluster, no periodic embedding, basically. Yes. And then regarding James's comment regarding fragment molecular orbital, I think there is an issue I raised a few months ago regarding the implementation of the fragment molecular orbital in AIMS. I'm not sure if it's resolved, but the last time I saw it, there's a shift in total energy. Yes, that's it. It's more of a comment.
All right, thank you. Okay. Any other questions from the audience? I don't see any at the moment. I also don't see any in the other streams. So, okay. Then I think we once again thank Gabriel for a very nice talk, as well as being here for the Q&A part. And I want to thank, of course, both our speakers again, both Andy and Gabriel, for taking their time to introducing all this explicit embedding work they've done within FHI-aims and also, of course, other packages. And I want to point out again before we close the session that we have the hands-on sessions tomorrow, both in the morning CET time, 9 a.m., as well as 4 p.m. CET time later on. Both sessions will essentially be the same. We have already seen on Gabriel's last slide that Oscar van Vuren will do a nice introduction to using FHI-aims in conjunction with ChemShell. And Gabriel will also give a brief overview again of his work on Embassy with FHI-aims. And also there's a tutorial coming, or there's already, let's say, a one in I would say beta stage, but this will be continuously improved on. And of course, I think also Andy and Gabriel will be in both of the sessions tomorrow to answer questions. So if you have any other questions related to embedding or to the talks today, please feel free also to join to ask these there. And with this, I would then close the session for today in the webinar. So thank you all again for being here. I hope you all enjoyed, and we will hopefully see you again soon. As always, look out on our socials, both on LinkedIn, YouTube, and so on. And of course, the webpage, FHI-aims.org, for mentions of upcoming webinars in this series. So thank you all again, and then hopefully see a lot of you tomorrow. Thank you.